So in this last segment, we'll take a step back and we'll look at some of the regulatory guidance for software verification and testing. We'll think a little bit about what the implications are for risk management and how risk management enters the process. And we'll give some outlined thoughts as to how one would develop a testing plan for a piece of software, a medical software package. So first we'll start where we start. We'll think about the risk classification of software. Remember the standard IC 62304 classifies software into low risk, class A, let's say medium risk, class B, and high risk, class C. We're not going to go through the details again, but the thing to keep in mind is that with increasing risk come increasing requirements both for the design and for the testing of the software. And actually here you'll see that the increasing requirements for the design are precisely to permit higher grades of testing directly. So continuing with a regulatory review, unlike coding, which is very sparsely covered in the regulatory documents, the documents dedicate significant space to testing, and this is what in some ways they're designed to do. The general description that we can see here, there are two main areas in the documents that we find descriptions of testing. The concepts of developer testing, and this is where the GPSV comes in, section 5.2.5, and then testing done at the user side, and that's the GPSV section 5.2.6. So these are the two basic kinds of testing. Testing the developer's done in the lab, and testing gets done at the user side. IEC 62304 divides the process into 3 steps: unit testing, integration testing, system testing. The two are very analogous, and you can see the sections in the standard. If you look at the flow chart for the process of the software design and implementation in the standard, you can see that the first 4 steps have to do with design effectively, but the last 4 steps, at least 3 of the last 4 steps, 5.5 software unit implementation, software integration testing, software system testing, so 3 out of the 8 steps have to do with testing, which gives you a sense of the importance of the topic. So what are the targets for testing? So how do we define what we're going to test against? Where is our testing specified? So unit and module tests are traced to the detailed design. And this is, of course, for classes B and C, where we in fact have a detailed design. So that's where that extra requirement comes from. You need a more detailed design to allow you to do a more detailed testing, because that is required for a high-risk device. Integration tests are traced to the high-level software design, where we know what the modules are and what they communicate with. And then system-level testing are traced to the software requirements. So, for example, if you have a requirement that says that the system needs to do a particular task in under 2 seconds, let's say it's a computational algorithm, that is where that is found. And so we can do a system-level test to ensure that that procedure happens in that amount of time. And obvious, as it should be by now, is that all this testing cannot be performed in the absence of these design documents. If you don't have a set of requirements, you can't do system tests. If you don't have software design, you can't do integration testing. If you don't have a detailed design, you cannot successfully do unit testing. I mean, you can test some units randomly, but you have no way of checking that you have all of them done. There are a few more comments worth looking at, and this is from the QMS document from the National Medical Device Regulators Forum. And let's just read a quote here. These V&V, verification and validation activities, should include clinical use environment, usability, instructions for use, etc., interoperability of components and compatibility to other platforms, devices, interface, etc., with which SAMD, software as a medical device, works, should be considered. So you should, in addition to testing in the lab, you should test in the real world and make sure that it's all integrated correctly. Many problems only appear in real-world situations, and that's a well-known scenario in software. And the software will need to interface with other software devices, and this interfacing must be testing. And in the real world, unlike the lab, other things appear. We could have network slowdowns, we could have network disconnections, we could have updates to other systems that cause all kinds of little issues. So this document reminds us that we need to test in the real world, and we need to test for interoperability of our software with everything else that's in there in that environment. And finally, just again, to sum it up, this is a different kind of integration testing. Here our software is in fact a module. We're used to, as in the case of fMRI, think of modules used to construct our software, but in a complicated workflow, our software is a module for the real world. Risk management and testing, we are always going to return to this topic. Testing may fail to reveal errors, problems with our software, and this is a major risk issue. If we are relying on testing to find what's wrong with our software, the risk involved is that that process may fail to do it. Software testing is similar to diagnosis. While we may be diligent in terms of looking for symptoms, we may miss them. That could be because of human error or because a symptom did not manifest itself during a particular examination. Software is deterministic, so we have bugs when a certain set of inputs gets applied to the software, and those may be very particular. So we may test many, many times, and those exact conditions may never happen. And then suddenly those conditions appear. So we may have done all the testing in the world, and the symptom, the bug, may not have appeared, but it may still be there. So that's some of the issues we have to worry about. Few more comments here. Unit and integration testing involve the writing of code for test cases. So this is code, may have errors in it. And testing code needs to be designed and reviewed with similar rigor to that used for the production code. Okay, it's code, you still need to design it, you still have to be careful. And then of course you end up in this ended loop of having testing code for testing code for testing code. Obviously you have to maintain some level of sanity here, but testing code should not be an afterthought. It should be written clearly and reviewed in the same way. Some final comments. We have to worry that whether a software is exposed to enough external conditions. If we have a complicated piece of software that does a very complicated non-linear procedure, having just one set of tests may not be enough. And the software should not always be tested by the same person in the same way. You hear the comment, it always worked for me, and that's always true for me, by the way. My code always works for me. You hand it to another person and it breaks down. Again, the problem is that because software is fundamentally non-linear and small changes in the input expose different functionality, when you have the same person doing the testing the same way all the time, those conditions are always present, and we fix them. We fix those paths through the software, but we'll be missing something slightly different. So having some element of randomness and changing how we do it slightly may reveal issues as well. What increases the probability of failure in testing? Well, inexperienced testers is one. Difficult conditions, they don't have enough information, we don't have enough data, and ill-defined tasks. If the testers don't know what they should be looking for, that means the testing is highly likely to fail with the resulting problems. So let's talk a little bit about how we create a testing plan for our software. What does this involve? The first is, well, for each requirement, you need to design a set of tests to demonstrate that it is met. So start with your list of requirements, create a set of tests, make sure it's done. You want to create tests for the entire workflow end-to-end, where the user is asked to mimic a real-world procedure situation, and this test may involve replicating previous measurements. So here's an image, follow the 10 steps that a radiologist would follow to create a measurement, and do this over and over again to ensure that we get the right answer. You want to add a set of random operations, have the tester play to see if anything breaks. This is part of trying to find out more about the software by just poking around. And a good description of all of this testing setup will involve plenty of pictures, right? So you need your tester to have pictures. If you click, this is what you should see. And if you don't see exactly what's on the screenshot, please flag it. You may be seeing something interesting. Let me highlight one more thing about the random operations part. And you see that in a previous problem, we talked about prostate biopsy a couple of segments ago as an example of a procedure. The way prostate biopsy is done in many hospitals right now is that we have MRI images of the patient ahead of time. Those get used to identify lesions which are targeted for biopsy, where a needle is placed in the middle of that lesion to extract a small piece of tissue to see if there is cancer there. But in addition to that, the urologist will actually do random sampling of the prostate. They would poke at different areas and extract a few other samples when there is no necessarily visible lesion there. And the reason for that is, again, this randomness often helps. If there may be cancer there that we can't see, there may be a bug there that will not be revealed by our standard testing. And so some randomness helps the process. Continuing with the testing plan, it's good to have regression testing for the automated parts of the processing, so tests that exercise the code automatically, run it against previous inputs and compare the results to previous outputs to make sure that nothing broke due to changes. And ideally, one should be able to execute the same executable that the user uses in test mode. So all the inputs provided as part of some command line, and we obtain outputs that can be compared to previous silver standard results. And this is important because, often when we write small tests, we link to the library, we exercise a function or two, and that's useful. It exercises a piece of code, but being able to run the full executable, again, we're approaching the real world situation. The software is initialized, the memory is allocated. We may find bugs that only happen when the full executable is loaded because it stresses the system in a different way. And this is the final point. You want to test the actual executable as much as possible. There is no substitute for the real world, the real executable, the real conditions. In addition to what we've talked about, and this assumes our focus so far has been more on the computational side and the low-level side, we want to do user interface testing, and we talked about this as part of our description of usability in week 7. and we want to do cybersecurity testing, for example, penetration analysis, to see if one can hack into the system. We reviewed cybersecurity briefly in week 3. Finally, one wants to test for desirability. Okay, so do our users like the software and do they enjoy using it? User delight is not really a regulatory requirement. The FDA won't tell you your users must love your software, but it can really be a make or break market requirement. If people don't like your software, they may never buy it. Desirability can be formalized. You can formalize through extra non-functional requirements. At the end of this, you create a test where you ask people to rate your software at 1 to 5. 1, they don't like it. 5, they love it. You say this software needs to achieve a score of 4 on this requirement to satisfy the specifications. And we also go about and obtain informal feedback from sort of beta testers and customers and all of those things. And just to summarize this story here, perfectly functional but clunky software will not necessarily sell. Nobody will actually be excited to show it to their friends. Here's this great tool that I'm using in my clinical workflow. You should be thinking about that too. And Dr. Khalid will come back and talk to you in week 12 of this class about the management process and how to engage users and how this whole process works from more of a management perspective. So this concludes our discussion of software testing, this lower level part of the lifecycle process. The next step is to talk about validation, where we do testing to see if the software satisfies the needs of our user. But before we do that, we'll go on a detour for the next week's segment to talk about math and probability statistics, detection theory, because those are required elements as we think about designing a validation plan. Thank you.